Moving on to our task number 3, which is completing our MPLS VPN configuration. And the goal of this is to provide connectivity for the customer C1 and C2 across our MPLS VPN. Okay, so far we already have the customer network prepped for this. Now we're going to have to complete the BGP configuration in the middle here. So first we have to configure a full mesh IBGP between R1, R2, and R4, which are our PE routers, to transport VPN v4 routes. We need to disable IPv4 BGP, makes sense because we do a VPN v4, not IPv4. And we must use BGP peer template since the configuration is going to be pretty much identical for each of the neighbor configuration. So just to be efficient. And then we need to source our BGP from the loopback, as we usually do when we configured IBGP. Okay, so let's run with that first, starting off with our router R1. And I believe our AS number is 100. Okay, so router BGP 100, no synchronize and no auto. Again, the standard BGP config with the router ID 172.16.0.1. So we need to disable IPv4, the default. So the command is no BGP default, IPv4 unicast, and then we go ahead and configure our peer template. If you're not familiar with the peer template, we have a separate BGP video that walks you through the concept of peer template, so you might want to check that out. There's our two types. So first is peer session. We're going to call this one PE. Okay, and what you can configure here are the basic remote AS as well as the update source. Okay, there's the bunch of other configuration you can do as well, but the ones that's required for our particular task here are the remote AS 100 and then update source loopback 0. Okay, now second type of peer template is peer policy. We're going to call it the same name, PE, and what we need from this particular template is the send community. As I mentioned, the route target is actually an extended community, so we need to make sure that all of our BGP neighbors are capable of sending an extended community. Okay, so now that we have the peer template, we can go ahead and configure our neighbor to inherit the peer template. So start out with our neighbor 172.16.0.2, which is our R2. The command to inherit the peer template is inherit. And then if you do question mark, you can see the only options we have here is peer session. Okay, if you've done this before, as far as the peer template, you might expect to see a peer policy here as well, but since we have already disabled the IPv4 BGP, the peer policy configuration is actually going to be configured under the address family at VPN v4, which we'll see in a second here. But for us, we only need to configure peer session at this time, and we also need the R4 for that. Okay, now we need to get under the address family. And if you've done where there's VRF Lite with the BGP, you might be familiar with IPv4 address family with the VRF option. But for the route that's going to be carried or transported across the MPLS VPN, those routes are considered a VPN v4 route. So we have to do address family VPN v4, and then you can just do unicast. Okay, the first thing you need to do, just like any other address family, is to activate their neighbor. So first R2, and then we do activate, and then we can go ahead and inherit. As you can see right here, the only option we have is peer policy because peer session has already been taken care of outside of address family, and that will be PE. Let me just do up arrow and then do the same thing for R4. Okay, so activate R4 and then inherit peer policy. And those should be all the configuration that we need. And that will be pretty much almost identical for all of our routers. So what I'm going to do now is to bring up a notepad and then copy these relevant sections. And we're just going to modify it slightly. So we have a peer policy, peer session, so these stays the same on all of the routers. Router ID for next router we're going to configure is R2. So we have to change it to R2, and then the peer is going to be R1 and R4. So this will be R1. We actually don't need this because it's part of the peer policy. So right here, R2, peer R1, R4, R1, R4. Okay, so I don't need that either. And we can just put no sync just to make sure, no auto, in case you're running on the iOS that doesn't have those options as a default. And let me copy that, jump over to R2, and then paste. Okay, so as for R2, our last router is R4, so we're going to change that. That should be 2, that should be 2, and then again, copy and paste. Okay, so let's do some quick verification from R1. If we do show MPBGP and then just summary, you can see that we have absolutely nothing because that's assuming IPv4 BGP, which we were not running. For our scenario here, what you need is instead a VPN v4 option. And then you can just do all, or you can, if you're only interested in certain VRF, you can just do VRF as well. Here we can just do all. So currently we have a VPN v4 BGP connection from R1 to R2 and R4. And you can also do a neighbor command. You can see here details, neighbor details for R2. Okay, we have a capability to transport VPN v4, and that would be advertised and received. Right, we can go over to R4 and do the same thing real quick. Show IPBGP, VPN v4, all summary. Same thing. R4 already has connection to R2 and R1. Okay, so that should be first part of the task. Now let's move down to the next line, which is advertise all PECE subnet into appropriate VRF. And then once those subnets are advertised, we're going to go ahead and trace the labels being used from traffic, or by the traffic from the 172.16.16 subnet to 172.16.27 subnet, which is this subnet right here, going toward the subnet right here. Okay, so start with the advertisement of the subnet on R1. And we currently have two interfaces. This part of one is C1 and the other one is C2. So in order to advertise the subnet into the MPBGP, we get under the BGP 100. And then we need to get under the address family. Since this is part of a local VRF, we have to do IPv4 and then VRF C1. So for C1, the network is 172.16.16.0 with the mask /24. And then do pretty much the same thing for C2, which is 172.16.18/24. Okay, we'll come back and take a look at as far as what that route looks like, but let's go ahead and complete router R2 and R4. So on a router R2, we have a router BGP, and I believe router R2 has the VRF of C1. So address family VRF C1, network 16.27.0 mask 0. Okay, and the last router is R4 that has the VRF of C2, network 104.0.0. Okay, so at this point, all of the subnet that belongs to VRF C1 and C2 should be advertised across the MPLS VPN. So let's go and verify that starting at R1. So we can do show IPBGP VPN v4 all. So that will show you the whole routing table for both, for actually all of the VRF. So the first one is VRF C1. As you can see, the local route, which has the weight of 32.768 and the next top of quad 0. Those are local route with the VLAN 16, and this also has received a route that belongs to the same VRF on the other side coming in from R7 or R2 R7 CEPE, which is 172.16.27, and those are identified, or that is identified as a IBGP routes. Okay, same thing with the VRF C2. It has a local route of 172.16.18. and it has received a remote route of 172.16.104. So you can see the route has been successfully exchanged. Now if you kind of look deeper into the route itself, these are now considered an IPv4 route. So show IPBGP VPN v4, all 172.16.16.0. So these are the local routes. Let's make a note that right here, instead of just a regular prefix, it's actually been prepended with the route distinguisher, as I mentioned earlier. The route distinguisher makes a VPN v4 route unique. So that way if you have a overlapping or the same prefixes being used between different customers, you make sure that those routes stay unique because different customer will be having a unique route distinguisher assigned to them. Okay, so I want to make a quick note as far as the extended community as well, which is route target. So the route has been tagged as part of the route target export with the route target of 100, 100. So along with that, the router R1 also has assigned a MPLS label, a local label of 25 for this particular route. So you can see right here in, so that's for input 25, and because it's a local route, there's no output label. Okay, so that's actually another method of exchanging an LDP or MPLS label. LDP was one of them, was one method, but for MPLS VPN, BGP, or to be exact, is the multi-protocol BGP is used by a router to advertise the MPLS label. So on every PE routers, each of the prefix on each VRF has a label assigned to it, just like how the regular MPLS router has the label assigned to its route in its unicast routing table. Okay, so let's take another look at the remote routes. So we just look at the local routes, .16. Now let's take a look at .27. Okay, so same thing, the route has been prepended with the RD of 100, 100, and extended community, these are being received by R1 from R2. Okay, and along with that route is a label, MPLS label 24. Okay, so for R1 to send traffic to this particular subnet, it will basically impose a label of 24 to the packet, which we will see when we do the packet capture. Okay, it's just for the sake of completeness. Let's do a show command for C2 as well. So C2, you can see how the route distinguisher changed to 200 to 200. Route target has changed as well, and then the local label for that is 26. And the last route is 104. Again, C2, 200, 200, 200, 200, and then the remote label is 23 for that route. Right, so now let's do a show MPLS forwarding VRF C1. So just want to see what it looks like when R1 needs to send traffic towards the VLAN 27 subnet. And this is kind of stepping into the task for tracing the label used by the traffic from VLAN 16 to VLAN 27. Okay, so let's see what that looks like. So R1 do an MPLS forwarding based on VRF C1 16.27.0. You can see the outgoing label is shown as 24. Okay, and the prefix is 27.0, and V designate it's part of a VRF or is a VPN routes. And the next hop is a router R3, which is our P router right here. This is our next hop, obviously, from R1. But what this show command doesn't show you is the label stack, so we need to do a detail of the same command. So right here, now you can see the whole label stack that will get imposed onto the packet. So 24 is just the transport label, if you will, just to get the traffic from one PE to another, the ingress PE to egress PE. But what's actually identifying the remote prefix, or the destination prefix, is the, or actually 24 is, 18 is a transport label, and 24 is actually the true label for the destination. Okay, so here's a label stack that would be the bottom. That would be the bottom of the stack, and then 18 would be the top of the stack. So label 18 will get the traffic from R1 to R2, basically, and then on top of that you have 24, which is the VPN label. And if you recall when we did the show MPBGP command right here for 172.16.27, we're seeing that the label 24 was advertised along with the route from the router R2. Okay, to identify that particular prefix. And the other thing you want to make a note of is the MRU actually went down. If you've been watching our previous video, the MRU has always been 1500, which is the same as the interface MTU by default. But now since we're dealing with additional MPLS label, you can see how it gets reduced by 4 bytes because each MPLS label is 4 bytes long. Okay, so we know that as the packet leaves the router R1, it's going to have a stack of 18, and 24. Okay, so top to bottom, 18 at the top, 24 at the bottom. You can pretty much do the same thing with the show IP ceph VRF command, C1 192.16.27.0. Okay, you can see that the two label that gets imposed to the packets shows up right there, 18 and 24. So now we're going to trace this particular labels or these labels on the packets. So next hops is R3. So we're going to go over to R3 and then we're going to do show MPLS forwarding. We know that it's going to be coming in as label 18. So let's see how the R3 lookup label 18. Okay, so input label 18 or incoming label 18 is going to be outgoing or be swapped by the outgoing label 16. Okay, and that's being load balanced between the interface 000 and 010 because we have an equal cost path to get to R2 here. Okay, so R3 has an option to send the traffic that way or that way, but either way, it will swap the label 18 with the label 16. So at this point, the packet should become 1624. So the bottom label or MPLS label should never change. Okay, so 1624. Now let's assume that the packets, the R3 actually choose R5 for that. So we're going to hop over to R5 and we're going to look for MPLS forwarding label 16. Okay, and at this point the R5 will completely remove the label or top label while still maintaining the MPLS labels. As far as pop tag means removing the topmost label. Okay, and it's going to send out of 000 and that's towards R2. As you can see, that particular label is being used, or it should be used for getting to the prefix of A21602, which is R2 right here. Okay, so as it leaves R5, the tag 16 gets popped, so what is left is label 24. Okay, now finally the packet reaches the egress PE router with label 24, so we can try to show MPLS forwarding label 24, and you can see that R2 knows exactly that that particular packet is destined to arrive for the 172.16.27 subnet. Okay, it's also marked as a VPN v4 or VPN routes as well. Okay, and just to make a quick note, the behavior of removing the topmost label before it reach the final or egress PE router is what is called a penultimate hop popping or hop pop or PHP, and that way R2 doesn't have to do a label lookup twice. And in this case, all the R2 needs to look up is label 24 and knows exactly where the destination of that packet is. Okay, so now you should understand a little bit better as far as how the MPLS VPN packets gets transported across a MPLS core network, and how the MPLS VPN label plays a part in that. And just to reiterate, the label 24 is the label that R2 communicate to R1 as part of the BGP advertisement. So R1 knows what packets to, or what labels to impose before it pushed the packet into the MPLS. Okay, so next we need to make sure that the R6 can reach R7 and R8 can reach switch 1. But there should be no connectivity between the two customers' network. Okay, so what it means is R6 right here should be able to reach R7 and then R8 should be able to reach switch 1. Even before we do our connectivity test from the CE device, we can do a quick test between the PE to PE sourcing from the corresponding network. So let's try first for a customer C1 from R1 to R2. Let's do a simple ping for this. We need to source it from the correct VRF, which is C1, and then what we're trying to ping is 172.16.27.2, which is our IP of our 2 interface right here, and then enter. You can see that it's reachable. Actually, let me go over to R2 and then do a quick debug ICMP so you know exactly what source IP the packet's using. So it's the R2 is seeing the IP, or the packet is coming from the IP 172.16.16.1, which is our fast01.16 on R1. Okay, so that's basically proof that we have connectivity for that particular VRF across the subnet. We can do the same thing with R1 pinging VRF C2 172.16.104.4, which is our for fast Ethernet 0 interface. You can see that it's pingable as well. Okay, so now what we're going to need to do to test end-to-end connectivity is to start off by going into R6. So since we're not running a dynamic routing protocol between CE and PE, what we just need to do is to create a static routes on R6, point to R1, and to keep things simple, we're just going to do a default static on R6. So commands IP routes, and R6 has no idea about the VRF itself, so it doesn't have to reference any kind of VRF whatsoever. Okay? It's just the PE router that has the knowledge of the VRF configuration. All it knows for R6 is in order to send a traffic for anything for now, the next hop is going to be R1. Okay, and we have to do the same thing on R7 as well for the return traffic. So routes, IP routes, 172.16.27 for R7 is .2, which is router 2. Okay, now from R7, now you can just basically ping 172.16.16.6. You can see that it's pingable now. Okay, so we just ping R6 from R7. Now we're going to take care of the VRFC2. So we have to go into the R8. Same thing, IP routes, 172.16.18.1. And then our switch 1, IP route, 172.16.104.1. And for actually it's .4. Delete that. 4. And then do a ping 172.16.18.8. And that is pingable as well. Okay, let's go back to R6 real quick. And we know we were able to ping R6 from R7. And we should be able to ping R7 from R6 as well. 7, and that's is the case. Now we can do a trace route to that and see what happens. You can see how R6 sees every single hop. So it went from R6 to 13427. So it went 1, 3, 4, and then 2, finally 7. Okay, but if you're trying to ping from C1 to C2, which is R6, to, let's say, a switch 1, 104.10, and you can see that it's not pingable. In fact, it's receiving a unreachable ICMP unreachable for the packet because there's no such routes to this particular prefix in the routing table or that particular VRF routing table. Okay, so we have successfully tested connectivity between the two remote sites within the same VRF but not crossing the VRF. That takes us to our final items on our task, which is we need to run Wireshark packet capture on R1 fast 00 and review the MPLS VPN packet. So we're going to run Wireshark right here. Okay, so now let me bring up Wireshark, and we need to make sure that our switch has the span session configured. So let me make sure that's the case. Let's do show monitor session. Okay, so currently there's no span session on the switch. So our R1 fast 00, so that's what the interface is connected to a switch. Fast 01, so right here. Fast 01. So, and we have a Wireshark machine of a fast 023. So monitor session, source interface fast 01, and then destination interface fast 023. Okay, and here's our Wireshark capture that we have running. So what we're going to do now is to do a ping from R6, again, right here, to R7, and see what that packet looks like as it leaves router R1. Just going back to router R6, go up arrow, ping 27.7, there you go, 5 pings successful. You can see a batch of pings right here. Let me stop the capture. And let's go through the ping request packet, starting off with the Ethernet, since it's an Ethernet interface. Okay, we've seen this before in our previous MPLS video, where the Ethernet frame type for the next header is MPLS. And then we have, actually this time, 2 MPLS labels. As we anticipated, one should be 18, which is the topmost, which is right here. As you can see, it shows as label 18. Experimental bit is 0, since we're not actually dealing with QoS at this point. and then we have a TTL of 254. Okay, and then the next label or the bottom of the stack label, which is the MPLS VPN label. It has a label number of 24, as we again saw on our show commands earlier. And you can see, since it's the bottom of the stack, it also has a bits for the bottom label stack set to 1. Okay, and the TTL is also 254. Okay, and then after our bottom of the stack MPLS is just the regular IP headers with the R6 IP as a source and then R7 as the destination. And these are just regular IP packet header, time to live 254. Okay, this protocol ICMP, and then we have our ICMP payload for ping requests. Okay, so coming back the other way, reply. Although we didn't quite trace the labels on the packet coming from going from R7 back to R6. Okay, but we kind of talked about how on the last hop, the packets are the topmost label, and the packet gets stripped, and then we just left with the VPN label right here. So the same should be true right here, since this is right here is the last hop. As the packet comes into R1 for the ICMP reply, we have the label 25, and that's, I don't know if you remember when we did the show command on R1. Let's see if we can find that for right here. 172.16.16. It has the local label of 25 allocated for that particular prefix, and that's why when the traffic is coming back towards 172.16.16, it has the VPN label of 25. Okay, as the transport label, which used to be a topmost label, got stripped already because of the PHP action. All right, and then it's just a regular ping echo reply. All right, so that's pretty much the structure of a MPLS VPN packet, and that concludes our task number 3. Okay, so what we've looked at so far in this lab is just the very basic configuration of MPLS VPN. We haven't even dealt with the dynamic CEP routing protocols yet. And things like the more advanced MPLS topology or even the share services, those are something we're going to be looking at in our future videos. But the most important thing is you guys have a good understanding of this technology in its most basic form before proceeding to a more advanced and complex configuration. Okay, so that's pretty much wraps up our video on MPLS VPN fundamental. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMinutes.com, and I'll see you guys in the next video.